We had just worked out the empirical formula and the molecular formula for adipic acid. And now we're going to start talking about writing chemical sentences. In other words, how to write a chemical reaction so that you know what you're doing and anybody else that looks at it knows what you're doing or what you did. And the format is simply on the left, you put the reactants with an arrow with the products. And that's typical. And eventually, we're going to get to the point where we can show that reactants lead to products, but products can also go backwards and lead to reactants. But for now, we're just going to have one arrow going from left to right. And we'll worry about the backward reactions later. In this example, we have a compound, C2H5OH, which is ethanol. That's the drinking kind. And we're going to burn it. So that means we're combining it with oxygen, O2. Remember, O2 is one of those diatomic elements, like hydrogen, nitrogen, oxygen, fluorine, bromine, iodine. Those are all diatomic. In other words, when you see them in a word problem saying this reacts with that, if it says oxygen reacts with ethanol, then you have to write it O2. If you don't write it O2, then the equation will never balance, which I haven't shown you yet, but I will. And then the products that come out of that reaction, see, from the very beginning, chemistry was identified as the study of change from one substance to another. And here's a perfect example. We're going from ethanol, which has its characteristics, oxygen, which has its, and we're going to end up with carbon dioxide and water, which were completely different characteristics. They're new identities in the products, carbon dioxide and water. Okay, the way this equation is written, let me go ahead and put it up here. C2H5OH plus three oxygens. Yep. Three oxygens yields carbon dioxide and water. There we go. Two here and three there. And the way this is written, what we're saying is one possibility that we're saying. This molecule, this one molecule of ethanol reacts with three molecules of O2 and yields two molecules of carbon dioxide and three molecules of water. That's one way to look at it. Once you have written these reactants and products correctly, and that's what we spent time on so far, is writing compounds correctly. Once you've written them correctly, once you put them in the equation, you can't change those subscripts. They're chiseled in stone. The only way you can change the number of atoms so that you have a balanced equation is with coefficients. And if there's no coefficient out here, there has to be a 1. We don't write the 1. That's redundant. So in order to satisfy Dalton's theory of atomic theory and conservation of mass from Lavoisier is to have the same number of atoms of each element on both sides. So let's see if we do. 2 carbons on this side, right? That's it. 2 carbons on this, because 2 times whatever's in here. 2 times 1 is 2. This one has 6 hydrogens. 2 times 3 is 6. And 1 oxygen here and 6 there. So that's 7 oxygens. So we have 4 oxygens here, 2 times 2, and 3 here, that's 7. So this equation is balanced as written. That's one interpretation. Individual molecules and atoms that you're saying are going in that reaction. The more useful way is to think of it in terms of moles. 1 mole of ethanol plus 3 moles of oxygen yield 2 moles of carbon dioxide and 3 moles of water. That's something we can sink our teeth into. Okay, eventually I'm going to show you how to do that, how to balance it. I got a method. And these ratios, these values here, 1, 3, 2, and 3, are ratios of each of the reactants and products. So if we know that we have, say, 4 moles of carbon dioxide, right? That's what we want to end up with, 4 moles of carbon dioxide. Then we can convert that carbon dioxide to oxygen and say, this is how many moles of oxygen are required to give you 4 moles of carbon dioxide. Once you got that balanced, then the ratios here, in terms of moles, are 2 to 3. Now we can say 2 into 4 is 2, and 2 times 3 is 6. So we actually need 6 moles of oxygen in this reaction to give us 4 moles of carbon dioxide. So these coefficients actually give you conversion factors for doing stoichiometry. All right, we'll use those again later. Okay. I put these steps in here just so that they'd be recorded. I'm going to show you how to use them in a minute. So we're not going to focus on the individual steps. We're going to do it. We'll make this point, though. In your book, when you come to the point in chapter 3 where it says, write out your equation this way and then balance it by inspection. You know, you may wonder to yourself, what the hell do they mean by inspection? And I say that too. That's typically what a chemistry book will tell you, and it won't tell you how to do it. Some of them some of the more modern ones are starting to do that. They're devoting space in the books to showing you methods for balancing. But all of the older ones never did. In fact, I had to learn it the hard way. I just bull my way through it and try to figure out methods. So the method that I've come up with, I'm going to give you. All right. These are helpful hints. And one of the handouts, here it is, Balancing Chemical Equations, helpful hints. This one has the helpful hints that I'm going to put on the board and use. So we're not going to stop there either. That's just for recording. And we're going to use these helpful hints for balancing equations. All right, there's another one. All right, here we go. All right, now, this one at the bottom is probably a little too advanced. Let's use something simpler. I'll tell you what, let's use this equation unbalanced and balance it. How about that? Well, let's write it up here, unbalanced. What do you do first? You find out what your reactants are, what your products are, and be sure you write the formulas correctly. So this one is C2H5OH. Now, why do we write it that way with the H over here and the H over here? Well, because this gives you a little idea about the structure. Right? If I wrote this out in more complete form, this would be CH3, CH2, let's see, then with an oxygen and a hydrogen, like that. That way we can tell that this thing is ripe for hydrogen bonding. But we typically write it this way. Okay, then we're going to add oxygen, and our products are going to be carbon dioxide and water. Most of the time, you're given the products because the products in a chemical reaction are dependent on the reaction conditions. Right? You have high pressure on the gases, you have high temperature, low temperature. Those variations in conditions can affect the outcome. There are only a few cases where you should be able to deduce the products. And when we get to those points, I'll show them to you. All right. So we know what to expect. This is my budget method. I usually write it, string it out. So I've got a place in here for coefficients. I can write the coefficients in later or as we proceed. First thing you do is an inventory. What do you have on either side? We have carbon, we have hydrogen, and we have oxygen. Those are the only three elements that are in the reactants and products. So on this side, we have how many carbons? We have 2 to start with. And we have 5, 6 hydrogens to start with. And we have 1, 2, 3 oxygens. So that's our beginning inventory. And you can check yourself to see if you did it right. Right? That's 9, 10, 11. There should be 11 atoms in here. That's 2, 3, 4, 9, 11. Okay. On this side, we have how many carbons? 1. And hydrogens, we have 2. And oxygens, we have 3. Okay. First hint, helpful hint from that document is if reactants or products, if there's a lone element anywhere in your reactants or products, do that one last. So we've got an oxygen here. We're going to save oxygen till last, even though oxygen is balanced right now. And that's the beauty of the budget method that I've got is you can see instantly if you're balanced. We see instantly we're not balanced. Okay. So where do we start? Well, with practice, you develop sort of an intuition of where's the best to start so that it takes fewest steps. But if you don't know, just start at the top. They're not balanced, so let's start with carbons. All right, so we need 2 carbons on that side. How do you get them? You have to use a coefficient to give you 2 carbons. Remember, you can't mess with the formula. So that gives you 2 carbons. It also changes the oxygens. That's why we save this one till last, because any coefficient you put in front of that only changes that one. So now we've got 2 carbons here. What have we changed? We changed oxygen. So there's 4, 5 oxygens. Okay. So now we're going to move to hydrogens. Hydrogens, we've got 6 on this side and 2 on that side. Hydrogens is only in one place. That's good. So if we put a 3 here, that makes 6 hydrogens on that side and 6 on this side. So now we need to deal with the oxygens. All right. Oxygens occur in 2 places here. They're there, they're there. But here it's only 1 place, which is good. We need 5 oxygens on this side. We already have 1 here. So if we multiply that times 2, that'll give us 4 plus 1 is 5. Right? Okay. Now we're balanced. All right. Now we're going to look at this one. I've animated this one, so I shouldn't have to put it on the board. Here we have ammonium phosphate in solution reacting with calcium chloride to yield calcium phosphate and ammonium chloride. And in this case, we're specifying the phase, right? Solid, liquid, gas, or aqueous solution. That's important for this type of reaction. And you can either take my word for it or you can check it out to see if it's balanced correctly. Right? Phosphate is 3- charge. It's a polyatomic ion. Ammonium is a +1 charge, so we need 3 of them to balance that. Calcium is an alkaline earth, 2+ charge always, with a halogen, which is a -1 charge, so it takes 2 minuses to balance that 1, 2+. So you can check it yourself just to be sure. Now, the next thing I've got is my budget. Here's another trick, or another useful hint. If you have a polyatomic ion on the reactant side and the product side, And it hasn't changed in the process. In other words, you don't take the polyatomic and bust it apart, right? It stays intact through the reaction. You can use that as a balancing group. And that's what I've done here. This NH4, and I left the charge out for convenience. NH4 is here. It's also over here and nowhere else. So we're going to use it as a balancing group. Phosphate's the same way. PO4, I should have subscripted that. That's a boo-boo. PO4 here, PO4 there, no place else. Right? So we're good there. And then we've got calcium and chlorine. So first thing to do is the initial thing is to inventory. So we have 3 ammonias on the left-hand side, ammonium. Right? We have 1 phosphate, we have 1 calcium, and 2 chlorides. Okay, so far. All right, let's do the other side. Okay, there's 1 ammonium on this side, ammonium chloride. There are 2 phosphates in calcium phosphate. There are 3 calciums and 1 chloride. So we can see right there that it's not balanced. So where do we start? Well, there's nothing in there that's a single element, so we can't hold anything till last. I think what I did was start with calcium. And that's just my choice. Some places you start will take fewer steps. Sometimes it doesn't matter. But if you follow the rules and you keep track of everything in your budget, no matter where you start, you're going to end up in the right place. It just may take more steps depending on where you start. So I started with calcium, right? And I've identified the steps in that red mark that says step number 1. Put a 3 in front of the calcium chloride. Right? So that changes calcium to 3. It also changes chloride to 6. Okay. Now what do we got left? Well, we changed chloride, so why don't we go on the right-hand side and fix the chlorides? All right, so that's what we do next. We want 6 chlorides. I need a coefficient of 6. But that changes the ammonium. So now we have 6 ammoniums on the product side. So we're going to go back to the reactant side and fix the ammoniums on the reactant side. Oh, I got to do the chlorides first. Sorry. There we go, 6 chlorides. Okay, now we're going back to the reactant side and fix the ammoniums, because now we got 6 on the right and only 3 on the left. So that's my third step. All right, I put a 2 coefficient. That gives me 6 ammoniums. Okay, it also changes the phosphates. So 2 times 1 phosphate is 2 phosphates. Now you can see we're balanced. 6, 6, 2, 2, 3, 3, 6, 6. That equation is balanced. And I think I just fill in the rest to be complete. Okay, that balances our equation using the polyatomic trick. Now, if you run into an equation where the polyatomic is broken apart in the reaction, you can't use that trick. Even if you keep some of them in the product side and the rest of them, and you have some of them that are broken apart, then you got to go element by element. All right. What we try to do is produce an equation with the smallest whole number ratio of coefficients. So if you end up with a ratio like this bottom one, 4, 10, 4, and 2, we would prefer 2, 5, 2, and 1. So instead of 4, we want Roman numeral 2. That's the preferred format, at least for now. We're going to encounter places where we use fractional coefficients, but those are special cases, and we haven't got there yet. All right, this would be true, but it's not whole numbers. And this would be true, but it's multiples. Right? So we prefer the simplest whole number ratio. And of course, Roman numeral 1 is wrong. It's just not there. Okay, Which of the following are true concerning balanced chemical equations? There may be more than one true statement. The number of molecules is conserved. Is that true? No, because molecules says that the coefficients have to be the same on both sides. And it's not necessary. No, so one is false. Coefficients tell you how much mass of each substance you have. Is that true? No, it only tells you numbers. Mass is a different problem. In fact, mass is the problem that chemists didn't overcome until the latter part of the 19th century. And if we have time, I'll tell you that story. Number 3. So we got 2 false ones so far. Atoms are neither created nor destroyed. Yep. That's always been true. Still is. Coefficients indicate the mass ratios of substances. Well, that's another way of saying number 2, and it's wrong. How about Roman numeral 5? The sum of the coefficients on the reactant side equals the sum on the product side. Nope. There's no guarantee of that either. So the only one that's true is this one, Roman numeral 3. Okay, just to hammer the points home, the number of atoms of each element in the reactant side have to be the same in the product side. You can't touch the subscripts. Once you've written the compounds correctly, can't touch them. A balanced equation tells us the ratio of the numbers of molecules which react and are produced in a chemical reaction. And the coefficients can be fractions, but for now, we're going to use the smallest whole number integer ratios. Okay. If we're going to do stoichiometry, we need a unit of measure that is something we can do in the lab. And we don't measure moles in the lab. We don't measure numbers of atoms. That's how the reaction occurs, at the microscopic level. But what we observe and measure at the macroscopic level is mass. So we need a bridge between the two in order to do stoichiometry. And that's where molar mass comes in. Now, we know how to calculate molar mass. Whether it's an element or a compound, we use molar mass. So here we got steps again for stoichiometric calculations. And they're up there so that they're recorded. But we're going to do an example. And if you like flowcharts, there you go. Okay, let's consider this one. And this equation is already balanced. P4 solid, which is a very reactive form of phosphorus. This is white phosphorus. And all you have to do is leave it out in the air and it'll react. In fact, used to be tons and tons of this stuff produced every year until the workers started going home ill and some of them dying. And this is the gas. And this is going to produce P2O5. That's a solid, I think. Yeah, solid. Okay. This one is already balanced for us, and we can prove it, right? 4 phosphorus, 2 times 2 is 4, and 10 oxygens, 5 times 2 is 10. So we know it's balanced. What we're given is 6.25 grams of phosphorus. Grams of that phosphorus are burned in the air, excess oxygen, all the oxygen you need. You're not limited at all by the oxygen. So all of this is going to be consumed. There's plenty of oxygen. Okay. What we want to know is what mass of oxygen is required to complete that reaction. Okay, here's how you do it. First of all, number 1 rule, there's a Great Wall of China right here, anywhere you've got an arrow or a plus sign, there's a great wall. You can't get over that wall unless you're in moles. You got to be moles. You got to be numbers. You can't get over there with mass. You can't go under, you can't go over. So we have to convert this to moles first before we can go anywhere in this reaction. So 6.25 grams of phosphorus is how many moles of phosphorus? Well, this is in the numerator, so we need grams in the denominator to get rid of the mass. But we need to leave ourselves with moles in the numerator. That tells you grams and moles in a quotient means molar mass. So what's the molar mass of P4? Well, we'll go over here and look at phosphorus. It's 30.97 for one. And you got four of them, right? So 28, 2 and 36 is 38, carry the 3, and 12 grams per mole for that formula. 123.88. Here we go. So that will give us my calculator. That will give us the number of moles that we're going to react of P4. 6.25 divided by 123.88. And that's 5.04. I'm going to keep a decimal. Throw it out later. 10 to the minus 2 moles of P4. Okay. Now we can move. Now we can use our ratio. 1 to 4 to 5 is the ratio of moles. So this allows us moles of P4, moles of oxygen. That's the ratio of these two in this chemical reaction gives us our conversion factor. So we have one of these and 5 of those. So all I have to do is multiply this value in my calculator times 5. That cancels this one and leaves us with moles of oxygen. So that's 2.523 times 10 to the minus 1 moles of oxygen. Now that we got moles of oxygen, we have to convert back to grams because the question is mass of oxygen. We now know the moles of oxygen. We've got to convert this to mass of oxygen. So this is going to be moles on the bottom, grams on the top. Remember when I said these conversion factors are always equal to 1, right? So if they're equal to 1, you can do them either way. In this case, we need moles on the bottom, so they'll cancel out, and grams on the top. So how many grams per mole of O2? 1 oxygen is 16. 2 oxygens is 32. Round to 2 decimal places. So that times the value is, and I'm going to keep 3 significant figures, 8.07 grams of O2 will be consumed in the burning of 6.25 grams of P4. Okay? That's how you do stoichiometry at our level. We're going to expand, but this is the beginning. If you've got grams to start with, convert to moles, and you can go over the top, convert to moles of either this reactant, or we could do it with the product too. We could determine how much product is going to be produced. All we'd have to do is change this conversion factor. Instead of 5 here, we'd have 2 P2O5. And we could do that. Then we convert that P2O5 using its molar mass, and we can find out, theoretically, how much P2O5 would be produced. Okay. Questions or frowns? This one? This is the molar mass of phosphorus. And you've got 4 of them. So the molar mass of P4 is 4 times that, right? Okay. That's our first exercise in stoichiometry. This one is a little more involved. Let's see if I got time to do it. A little after 1. I should have enough time. This ups the game a little bit. So we've got two reactions, two separate reactions here. Methane in oxygen is burned to produce carbon dioxide and water. And in another reaction, ammonia is burned in oxygen to produce nitrogen monoxide and water. First thing we're going to do is write the balanced equations. Let's do that. Methane plus oxygen. So let's see, let me go over here. Yeah, let me do one over here and one over there. So here's the methane plus oxygen produces carbon dioxide and water. Okay. Yeah, I stretched it a little much. Let me back it up some. Need to leave room for the other reaction. There we go. And the other one is ammonia and oxygen. Two separate reactions. Produce nitrogen monoxide and water. Yep. Okay, let's balance these equations. All right, since this is new to you, I'll go ahead and do the budget. Some of them, after you've done enough of them, some of them you can do without setting up the budget. I mean, you just obvious what happens. But in this case, we're gonna keep it legitimate. Carbon, hydrogen, oxygen. Those are the only three. One carbon here, 4 hydrogens, and 1 oxygen, right? So that should be 6. 2, oops, let me spell. 6, 7. Ooh. Good thing I checked. Okay, on this side, we've got 1 carbon and hydrogens, 2 hydrogens and 3 oxygens. Okay, so carbons are already balanced. We're going to keep oxygen, so hydrogens are only an option. So we need 4 hydrogens on this side. 2 times 2 is 4. We've changed the oxygens. 2 plus 2 is 4 oxygens. Okay. Now, all we need to do is have 4 oxygens over here. So 2 there gives us 4 oxygens. And that shows us we're balanced. Okay. Now I can erase it because I'm going to need this space down here for other stuff. Now that we've got a balanced equation, let's go balance this one. Nitrogen, hydrogen, and oxygen. 1 nitrogen here, 4 hydrogens, 2 oxygens. Here we have 1 nitrogen, 2 hydrogens, and 2 oxygens. I think that's right. 4, 5, 1, 2, 3, 4, 5. 1, 2, 6, 7. Yeah, that's right. Okay, nitrogens are already good. Hydrogens again. So we want 2 here. Right? That'll give 4 plus. Now we've got 2 oxygens and 1, so that's 3 here. All right. So how do we get 3 oxygens here out of that? Next trick. Intermediate step, use a fraction. Okay. So if we multiply this one times 3 halves, that should be 3 here. Okay, look at this. You got oxygen. That's the actual oxygen molecule. Got two oxygens. We only need 3 oxygen atoms, right? So if we multiplied that by 3, that would be 6, wouldn't it? 3 times 2 is 6. Well, let's take 6 and let's take a half of it. That's 3. Okay. So we've got 3 oxygen atoms using a fraction. Do I need to explain it a different way? Okay. Think of this as let's see. Okay, let's look at it as an algebra problem. Let's say we have 2 times x, and we want to end up with 3 on that side. Right? That's a valid algebraic expression, isn't it? Okay, so we know how to solve that, right? X equals 3 divided by 2, right? You didn't know there was so much algebra in chemistry, right? Thought you were out of when you got out of algebra class. Okay, that's not where we stop though, because we want whole numbers. This is an intermediate step. So now we have balance 3, 4, 1. We want to get rid of that half. This ratio is fixed: 1, 3 halves, 1, and 2. So as long as we, algebra again, as long as we do the same thing to both sides of the equation, then we're good. Multiply by something, divide by something. So what I'm going to do is multiply the whole thing times 2. So that'll preserve the ratio, right? 2 times 1 is 2. 2 times 3 halves is 3. 2 times 1 is 2, and 2 times 2 is 4. Okay, and we used our 2. So now the numbers are 2, 3, 2, and 4 instead of 1, 3 halves, 1, and 2. But the ratios are preserved.
Question.
Oh, I'm sorry. Thank you.
So which one right?
I got to start over. Yeah, I have to start over. All that writing for nothing, man.
Well, I was going to point it out, but I think you do what you do.
No, don't ever assume that. We'll start over again. Right? Nitrogen, hydrogen, oxygen. Okay, now we have 1 nitrogen. 1 nitrogen over here. Hydrogen's 3, 3 here, and 2 there. And we have 2 oxygens here and 2 oxygens there. So we're back to hydrogens. Okay. We got hydrogen in one place here and hydrogen in one place there. It's a good thing we did that because now I get to show you another trick. If you've got hydrogen here as odd and hydrogen here as even, the best way is to use 2 coefficients and cross multiply. So we bring this 2 over here. And this 3 over here. That gives us 6 hydrogens here, and 3 times 2 is 6 hydrogens here. Then we have to do the rest of them. Right? So that's 2 nitrogens here, and still got 1 there. And this has, we did the hydrogens, 3 oxygens plus 1 is 4. Okay. Now, if those elements occur in more than one place on either side, then it's a little trickier. So now, let's see. We want 2 nitrogens on this side, so let's do 2. And that gives us 2 oxygens plus 3 oxygens, it's 5 oxygens. Okay. Now we use the fraction trick because you need 5 oxygens over here. 5 halves gives you 5 oxygens. Okay, now we can get rid of the fraction. Multiply it by 2 again. So that makes this one 4, makes that one 5, makes this one 4, and makes this one 6. Okay. All right. So let's clean up the mess. That one needs to be a 4. This one needs to be a 5. This one should be a 4. And this would be a 6. There we go. Now that we've got balanced equations, we satisfied the first condition here. 6. And this one is 2, 2. Okay, that one's good. Now the question, what mass of ammonia would produce the same amount of water as 1 gram of methane? So we've got 1 gram of methane, and we don't know that. Now, these reactions are occurring separately. We're only connecting them mathematically through the amount of water. We want to know what mass of ammonia is required to make the same amount of water as 1 gram of methane. So what we can do is find out how much water would this produce, right? And then say, okay, we want to make that same amount of water over here, and then back figure to this one. See where I'm going with this? All right. So 1 gram of methane, remember, can't go anywhere without moles. So what we've got to do is convert that 1 gram of methane into moles. So what's the molar mass of methane? Well, carbon is 1201. And 4 hydrogens. Hydrogen is 1.01 rounded to 2 decimal places. So that would be 4.04. 16.05 grams per mole. Is 6.231 times 10 to the minus 2 moles of methane. Okay. Now we want to convert that to moles of water. All right, so I'm going to put it down here. And the ratio is, we want moles of water, and we've got moles of methane. That means methane has to be on the bottom, because this is in the numerator. That has to be on the bottom. And the coefficients tell us that's 1, and this is 2. So I just need to multiply that value times 2. 1.4, oops, sorry. 246 times 10 to the minus 1 moles of water. That's the number of moles of water that this reaction will produce, 1 gram of methane.
And you took the 6.231 times 10 to the negative 2 to get, then divided it by the 2 to get.
Times.
You times it by the 2.
Yeah, because this is in the numerator.
Okay.
This is in the denominator. 2 times that gives you this value.
Gotcha.
Now, the question is, how much of this, what mass of ammonia is required to give you the same number of moles, same amount, same number of moles of water that that reaction does? So now we've got, this is the same number of moles that we fit in here. So this goes in here, and we want to convert that to moles of ammonia. So we have moles of water on the bottom, because this is in the numerator, moles on the bottom to cancel, and then moles of ammonia on the top. And what's the ratio? Well, in this case, 6 water and 4 ammonia. coefficients, 6 and 4. Okay. So if I take that number times 4 and divide by 6, I get 8.31 times 10 to the minus 2 moles of ammonia. Okay. Question was, what was the mass of ammonia? Now we have to change it back to mass.
Hold on. Please, for a second.
Yeah, sure.
And you took the 1.246
Mm-hmm.
and you times it
Times that
by 4.
and divided by that. Yeah, this means times. This, just take this and put it
Yeah.
right
I was writing it on mine and I was making sure I was putting it right.
there. Okay. All right. So now to convert that to moles, we need molar mass of ammonia. Now we're going to take this times moles on the bottom, grams on the top, right? Because this is on the top. We want to cancel moles, leave grams. So what's the molar mass of ammonia? The nitrogen is 14.01 grams per mole. And 3 waters is 3.03 grams per mole. Add those together, we get 17.04. Okay. So if I multiply that times 8.31 times 10 to the minus 2, 4 times, I get, let's see, 3 significant, yeah, 3 significant figures. 1.42 grams of ammonia. So in separate reactions, we burn a gram of methane and 1.42 grams of ammonia, we get the exact same amount of water, mass of water. Let's see. How much of it did I put in here? There are the balanced equations. This gives us 0.1246 water. Yeah. That's the same as 0.1246 moles of water. And then we take that number of moles of water and convert it to moles of methane, which we did here. 8.31, yeah, 10 to the minus 2. And then convert that back to, oops, excuse me, to 1.42 grams of ammonia.
Now, where did you get the 30 from 30? Where did you get it from? I know you got
Each hydrogen is 1.01 gram per mole. We got 3 of them. I did that one in my head.
Gotcha. I just wanted to make sure.
Yep. Okay. That was a pretty tall order for your first jump into, or your second jump into stoichiometry. First one was fairly easy, straightforward. But this one stretched a little bit. Stretched a whole lot. The next concept is limiting reactants. In a chemical reaction, what we've done so far is we've balanced equations in the ideal. In other words, if we have a certain amount of A plus B as our reactant, it's going to produce a C plus D. We've got it set up so exactly the right amount of A and B are combined so there's nothing left here, and you produce only C and D. That's ideal. That's what we call a stoichiometric ratio. Exactly the right amount. As a practical matter in the lab, that never happens. For one reason, measurement uncertainty. You can never measure these exactly the right amount to give you a stoichiometric ratio. You can get close, but it's never exactly right. Simply because uncertainty is a fact of life. So we're going to get a handle on it by identifying limiting reactants. So what is a limiting reactant? In this reaction, let's say there's not enough B. Might be just a little bit less than we need. It runs out first, doesn't it? The limiting reactant always runs out first. And leaves some A behind. This is called the limiting reactant. This is called excess. In that previous reaction where we had phosphorus with oxygen, oxygen is excess. There's plenty of it. Phosphorus ran out, and that caused the reaction to stop. All right. This is some artist's idea of what's going on at the microscopic level. The stoichiometric mixture would have exactly the right amount of hydrogen combined with nitrogen. So the nitrogen is the blue, the double blue balls, and the hydrogen is these three. So the ratio is 1 to 3, 1 here and 3 there. So that ratio, stoichiometric ratio, says for every 1 nitrogen, you need 3 hydrogens. And if you've got a matchup for every one, right, if that nitrogen has 3 dance partners, then it's going to produce 2 ammonias. This would be a stoichiometric ratio. There's nothing left over of these. You only have product. This is the case where the limiting reactant is hydrogen. Right? So we've got these 2 nitrogens sitting out there with nobody to play with. They got no dance partners. Right? So what happens to them? They're left over. They're in the product mixture. We have ammonia made from the others, but now we've got excess nitrogen, and the hydrogen is all used up. Okay. Let's see. Let's see how many more slides. I want to be sure. Yeah, I think we'll have time to run through this. So look at these different reactions. Where a reaction is hydrogen, this is a gas, plus oxygen yields water. And under standard conditions, that'd be a liquid. Okay, so that says that 2 moles of hydrogen plus 1 mole of oxygen gives 2 moles of water. Let's see if that's correct. 4 hydrogens, 4 hydrogens. 2 oxygens, 2 oxygens. Okay, so it's balanced. Now, if we look at this and say, all right, which one produces the greatest amount of product? Well, let's see, 2 moles. If we have 2 moles, this is A. If we have 2 moles of hydrogen and 2 moles of oxygen, how many moles of hydrogen can we produce? Well, what's the ratio here? The ratio is 2 to 1. Right? For every one of these, you need 2 of those. So one of these is going to consume all of those and leave 1 mole behind. And it will produce 2 moles of water with an excess of 1 mole of oxygen. Okay, so these will be in the product mixture. Okay, how about the second? So this one produced, the question is amount of product. Okay, so in this case, we produce 2 moles of product. That's all we're interested in. As the equation is written, we're interested in how much water is produced. That one produces 2 moles. Okay, in this one, we've got 2 hydrogens and 3 oxygens. Okay, here we are again. It only takes 1 of those to consume all of these and make 2 of those. And now we're going to have 2 moles of oxygen left over. So far, they're producing the same amount of product, 2 moles of hydrogen and 1 mole of oxygen. That's the stoichiometric mixture, right? 2 to 1, 2 to 1. So this is going to produce 2 moles of water. 3 moles of hydrogen, 1 mole of oxygen. 3 moles here, 1 mole there. Now we switched. This was limiting here, stoichiometric there. Now this one is limiting because 1 mole of this consumes 2 of those, and we got 1 mole of hydrogen left over. But it still produces 2 moles of water. How about E? Oh. Each produce the same amount. Oh, well, that's it. All right. We can't just add the total moles of all the reactants to decide which reactant mixture makes the most product. What we have to do is decide which one is limiting and then base our calculations to produce products on that limiting reactant because it's going to run out. And when it does, the reaction stops. All right. We have examples and problems that you can work in the review document for limiting reactants. But I should have a slide in here, and I don't. I should have a slide in here on how do you actually approach the solution of a problem where you're given mass of one and mass of the other. In fact, if you've got 2 reactants and you're given A grams of this one and B grams of that one, if you're given exact amounts of each one, you can assume that one of them is going to run out. So then you have to find out which one. Let me do percent yield. I think that's the last topic in this chapter. And if we have time, we'll work an example. Right? Otherwise, we'll have to wait until we look at the review documents and work those out. And in the meantime, you can go in there and work limiting reactant products and see how I did it with the handwritten version. And basically what we're trying to do is decide which one runs out. I'll give you a hint. If this is going to produce C and D, then you take this one, convert it to moles and say, how much product will it produce? C or D, it doesn't matter. How much product will it produce? Right? Then you go in and do B and say, if this is all used up, how much product will it produce? And the one that runs out first is the one that produces the least amount of product. Then you can go back and say, okay, all our calculations now are going to be based on the limiting reactant, and it'll go from there. So that's where we're going with limiting reactant problems. Okay, percent yield. As a practical matter, you know, not only that one is going to run out, but there are other factors that are limiting the output of your reaction. And every chemical engineer knows that, and they try to get as much out of a reaction as possible. They know the theoretical limit. Right? We've already done that. And they know limiting reactants. But there are other factors that have to be considered, like you're going to end up with a mixture, and if you want one of those products out of it, you got to clean up the mixture. You got to extract it somehow, separate it from the other products. And that step itself will not be 100% efficient. You're always going to lose some somehow. That's one possibility, the cleanup step. The other possibility is you think that this reaction is going from these reactants to those products, but maybe your conditions are not as closely controlled as you think they are. And you actually produce side reactions, produce different products. And that bleeds off what you would expect. So that reduces your output. Right? Those two are major factors. And for a chemical engineer who's working for a company, it's all about, the dollars. You make as much out of that reaction as you can. and keep your bosses happy. That way you get to keep your job. So one way to express it is percent yield. If you have a theoretical yield, which you get from the balanced equation, right? We've done that. Then you actually run the experiment and you identify the amount of a product that's produced and compare those two, the actual yield to the theoretical yield times 100. The ratio gives you a percent yield. All right. Let's see. Here we got a problem. I think this is the last one. Yeah. So I think we got just enough time to do this one. So in this one, we've got P4 again. And we're going to react with fluorine, 6F2. It's already been balanced for us. Isn't that nice? 4PF3. So let's see, is that right? 4 P's, 12 fluorides. Yeah, we're good. That's a gas. Okay, that's the balanced equation. The question is, what mass is needed? What mass of that is needed to produce 85 grams of PF3? So this is the actual yield. You want to guarantee that you have that yield if you know that the reaction has been optimized to produce 64.9% yield. At 64.9% yield. All right. So we can't use this equation until we get the theoretical, because this equation is based upon the theoretical. So what we have to do is say, all right, how much theoretical yield do we need in order to work from this mass? So take the equation, and the equation says actual over theoretical times 100. In this case, it's equal to 64.9%. Okay? We know what the actual is, right? 85 grams. So now we have an equation in one unknown, right? And you can solve any equation in one unknown. You can solve it. So if we move this one to the other side, theoretical yield, and we have 85 grams over here times 100, right? And then this one, numerator here, denominator here, 64.9. Okay, then we do that calculation. Right? 85 divided by 64.9 times 100 is 130 point. Let's see. I'm going to keep a few decimals to avoid rounding errors. 130.7. Right. So that's the theoretical yield that we need to guarantee this much actual. And prove it to yourself. What's 64.9% out of 130.97? It's 85.0. Right. What's the fractional value? 0.649. So it's over half of this. So half of that would be like 65, 66. And then you go up another 10%. Yeah, it's pretty, estimating. It's pretty close. So now we're working from here. 130.97 grams. We want to convert that to moles because in this equation, we can't go anywhere without moles, correct? What's the molar mass of PF3? Well, let's see. Fluorine is 19.00. Rounded off to 2 places times 3. And then phosphorus is 30.97 times 1. Let's add those together. That would be the molar mass of PF3. correct?
You don't add the 4.
Oh, no, not when we're doing these calculations. This is only for conversion factors. As far as calculations go, yeah. Good question. 30.97 plus. Okay, this is 87.97. So this, we need 87.97 divided into 130. Let's see. Yeah, it's already in my calculator. I just hit the button. 1.489 moles of PF3. So let's see, we have 1.489 moles of PF3. Now we want to use coefficients to convert PF3 to P4. We have 4 here and 1 there. So we just divide by 4. Okay. And I get 0.3722 moles of P4. Okay, almost there. Now we need the molar mass of P4. So let's see, this was phosphorus, wasn't it? So we need 30.97 times 4. Which is 123.88 grams per mole. And the next step is to take this value, moles of P4, and convert it to grams. So moles has to be on the bottom, grams at the top. And that's 123.88 times 0.3722, which is rounded off to, let's see, three significant figures. 4.6, excuse me. Standard notation. 46.1 grams of P4 will guarantee 85 grams of actual yield, considering 64.9% efficiency.
You were everyone.
Yeah, I know, I move all over the place. Are you writing it down though? Okay. And it's on video. You go back and look at it. Let's see if I did it right. Hold on a second. After all that trouble, there it is in steps. There we go, 46.1 grams. Sometimes I do these and I don't come out with the same answer. So then I ask myself, is it that or is it me? So then we go back through it and see, okay, find out where the mistake is. Sometimes it's me and sometimes it's that.
How do you even find which step you would have messed up on? Because you're all over the place.
Yeah, that's a good point. I need to be better organized on the board, don't I?
A little
Yeah.
Oh, there's somewhere there, right?
bit.
Yeah. So what I did was we started here and then we worked.
We started on the left.
We started on the other side.
Well, yeah, we put that in there. And then we put this here at that percent.
Yeah.
And then we figured out, all right, here gives us the actual amount we need. I mean, the theoretical amount. And then we said, okay, how many moles is that? Okay, here's the moles of that. And then we say, okay, if that's the moles of that, then this calculates the moles of this. And then we take this moles of that, and that gives us the output. Sometimes I'm a little more organized than others. Today I'm a little loopy. Okay, that's enough for today. What we'll do on Tuesday is get chapter 4, and we're going to talk about stoichiometry and different types of chemical reactions and then in solutions. And I hope we can get done before the lab starts.
So this is just for us to read over until Tuesday, right? There's nothing we need to do yet.
Yeah, you need to prepare your lab notebook. Yeah. There's also probably in Brightspace, what you're going to find is a discussion video. So look in 103, not in 101, but 103 for this lab. Look in that module and look for a discussion video. And then we may not have to do a discussion in class. Just have questions about the procedure. Yeah, of the lab. Yeah. Let's see, stop the share.